the cosmos is a graveyard, littered with the remnants of once shining stars. From the fiery heart of a massive sun to the gentle fade of a star like our own, the universe constantly orchestrates dramatic final acts. These spectacular deaths forged the most extreme objects we know, from shimmering white dwarfs to enigmatic neutron stars, and the ultimate cosmic devourers, black holes. Understanding these stellar finales reveals not just destruction but also the very origins of everything around you. Every star eventually runs out of the nuclear fuel that powers its immense glow. Its ultimate fate is sealed from the moment of its birth, dictated almost entirely by its initial mass. Stars are in a constant battle between the outward push of fusion and the inward pull of gravity. When fusion ceases, gravity inevitably takes over, leading to a dramatic transformation. This cosmic dance of life and death is fundamental to the universe's evolution. Our own Sun, a relatively modest star, will one day face its own demise, though not for another 5 billion years. It currently fuses hydrogen into helium in its core, maintaining a stable equilibrium for billions of years. When this hydrogen supply dwindles, gravity will begin to slowly win, initiating the Sun's spectacular transformation. You're witnessing a star in its tranquil middle age right now. The stellar life cycle, from birth in a nebula to its final remnant, spans timescales almost incomprehensible to us. Some massive stars live for only a few million years, burning brightly and briefly before collapsing. Smaller stars, like red dwarfs, can theoretically live for trillions of years, outlasting the current age of the universe. This vast spectrum of stellar lifespans paints a picture of cosmic diversity. Stars with masses similar to our Sun enter a red giant phase after exhausting their core hydrogen. The Sun will swell to engulf Mercury, Venus, and potentially even Earth, becoming hundreds of times its current size. Its outer layers will cool and expand dramatically, giving it a characteristic reddish hue. This transformation will be a spectacular and terrifying sight for any distant observer. As the red giant expands, its core simultaneously contracts and heats up, eventually reaching temperatures hot enough to ignite helium fusion. This new energy source temporarily stabilizes the star again, but for a much shorter period. It begins fusing helium into carbon and oxygen, creating new, heavier elements in its heart. This process is crucial for enriching the universe with building blocks. Near the end of its life, a sun-like star gently expels its outer layers into space, forming a beautiful structure known as a planetary nebula. A prime example is the Cat's Eye Nebula, a complex and stunning cloud of gas illuminated by the dying star at its center. These nebulae, despite their name, have nothing to do with planets. They are merely vast shells of gas. They are temporary, lasting only tens of thousands of years before dissipating. The exposed core left behind after a planetary nebula forms is a white dwarf, a super-dense stellar corpse. Sirius B, the companion to the bright star Sirius, is a well-known white dwarf packing the mass of our Sun into a sphere the size of Earth. It glows from residual heat, slowly cooling over billions of years. Imagine something so dense that a teaspoon of its matter would weigh tons. There is a strict upper limit to a white dwarf's mass, known as the Chandrasekhar limit, which is about 1.4 times the mass of our Sun. Beyond this threshold, electron degeneracy pressure can no longer withstand the immense gravitational buoyancy to withstand the immense gravitational pull. Any white dwarf exceeding this mass will face an entirely different and explosive fate. This limit defines the boundary between two dramatically different stellar endpoints. If a white dwarf in a binary star system accretes enough material from its companion to surpass the Chandrasekhar limit, it can reignite in a runaway thermonuclear explosion. This catastrophic event is known as a type Ia supernova, one of the brightest phenomena in the universe. Like SN 2011 feed in the Pinwheel galaxy. These standard candles are so consistent in their brightness that astronomers use them to measure cosmic distances. Such an explosion entirely obliterates the white dwarf, leaving no remnant behind. Within the core of these red supergiants, a series of fusion reactions creates elements up to iron. Each successive fusion stage yields less energy than the last, requiring higher temperatures and pressures. When the star forms an iron core, it faces a critical problem. Fusing iron actually consumes energy rather than releasing it. Iron is therefore a cosmic dead end, marking the star's final moments of stability. If the collapsing core has a mass between about 1.4 and 3 solar masses, it becomes a neutron star. These incredibly dense objects are composed almost entirely of neutrons, packed so tightly that a sugar cube of neutron star material would weigh billions of tons. A neutron star is essentially a giant atomic nucleus only about 20 kilometers across. Its density is so extreme that if you could hold a piece, it would instantly bore through the earth. Many neutron stars rapidly spin and emit beams of electromagnetic radiation from their magnetic poles. If these beams sweep across Earth, we detect them as regular pulses, earning them the name pulsars. The Crab pulsar, remnant of a supernova in 1054 AD, rotates 30 times per second, sending out precise flashes. These cosmic lighthouses are some of the most accurate clocks in the universe. Neutron stars are supported against further collapse by neutron degeneracy pressure, a force analogous to electron degeneracy pressure but involving neutrons. These neutrons are forced together so tightly that their quantum mechanical resistance to further compression provides the stability. This pressure is even stronger than electron degeneracy, allowing for even denser objects. It prevents the star from collapsing into a black hole, at least temporarily. Just like white dwarfs, neutron stars also have an upper mass limit, known as the Tolman-Oppenheimer-Volkoff limit, estimated to be between 2 and 3 solar masses. If a neutron star's core exceeds this critical mass, even neutron degeneracy pressure cannot prevent the inevitable. It will succumb to its own overwhelming gravity, leading to the formation of the most enigmatic objects in the cosmos. At the very heart of a black hole lies the singularity, a point of infinite density where all the mass of the black hole is theoretically concentrated. Here, the laws of physics as we understand them break down entirely, making it one of the most mysterious places in the universe. It's a place where space and time cease to have their usual meaning, challenging our very comprehension. Beyond these stellar remnants, supermassive black holes, millions to billions of times the Sun's mass, reside at the centers of nearly all galaxies, including our own Milky Way with Sagittarius A. While their origins are still debated, they play a crucial role in galactic evolution. These behemoths are not formed from single star deaths, but represent a different, grander scale of cosmic mystery. The death of stars, whether gentle or violent, is not just an end, it is a profound beginning. Supernovae, in particular, are responsible for forging and dispersing most of the heavy elements in the universe, including the carbon in your body and the iron in your blood. You are literally made of stardust recycled from the explosive deaths of ancient stars. These processes seed the cosmos with the ingredients for new stars, planets, and even life itself. Did these cosmic finales leave you in awe? Hit that like button if you learned something new about the incredible lives and deaths of stars. Don't forget to subscribe for more journeys into the wonders of our universe, and tell us in the comments which stellar remnant do you find most fascinating.